I mean, Oleg doesn't need introduction, but let me say that I'm very pleased to introduce his lecture. I have enjoyed it so far enormously, so I'm looking forward to enjoy even more today.
Thank you very much, Marta. So today I will continue what we have started the last time. So the last time we have considered a Riemann-Hilbert problem on a circle, set on a circle, and this Riemann-Hilbert problem was characterized by a jump matrix J, which was supposed to be smooth, but otherwise there were no constraints on it. And this jump matrix was allowed to depend on some parameters. And we have introduced a tau function associated to this Riemann-Hilbert problem as this Fredholm determinant. In the Riemann-Hilbert problems coming from linear differential systems and isomonodromy, this jump matrix actually comes with a factorization. So we have this factorization of the jump, where psi plus and psi minus are, as usual, functions that can be continued inside and outside of the circle. And in the simplest cases, in the cases associated, for to Painlevé 6 and 5 and 3, so this factorization, psi plus, psi minus, can be found explicitly in terms of hypergeometric functions. Now, solving the linear system was equivalent to finding another factorization, which is this one, but this will no longer be our concern. So this we don't care about that. So the tau function, once we have this factorization psi plus, psi minus, it can be rewritten in a convenient way as a determinant on the whole space H of vector valued functions on the circle. So here you have some integral operators. And we finished by mentioning this variational formula due to Widom, which allows to identify so this object here with the isomodromic tau function, which was introduced by Jimbo, Miwa, and Ueno, that is with the solution of the isomonodromy equations. Now, this formula, it is actually easier to understand, or at least to remember, in the graphical form. So here on the left, we have a 4-point tau function, that is the Jimbo, Miwa, Ueno tau function of a Fuchsian system with 4 regular singularities. And this factorizes into a product of tau functions of 3-point Fuchsian systems. And so this is basically what gives you this. So this gives a constant, this gives this prefactor here. And there is this determinant and the determinant of an integral operator whose kernel is determined by the auxiliary Fuchsian systems that we have introduced. So basically what we have here and here are some hypergeometric expressions that you can write really explicitly. And this extends in an obvious way to Painlevé 5 and Painlevé, all three types of Painlevé 3, and to higher rank, and so on. Okay. Now, there was a recent interesting work by Harini Desiraju, who has managed to implement a similar ideology in the case of Painlevé 2. Remember that for Painlevé 2, the analog of this Riemann surface picture was this hexagon, and basically you can cut a hexagon into two quadrangles corresponding to two Hermite-Weber parametrices. But this, again, this will not be our concern today. So for us, the Riemann-Hilbert problem will be always set on a circle. So my first aim is to use this Fredholm determinant representation that we have over here in order to produce a series representation for the tau function. And the idea behind this derivation is actually very elementary. So if you have a determinant of identity plus some square matrix, then it is a classical formula. I guess it is called von Koch formula, which expresses this determinant as a sum of principal minors. Okay. So now in our case, we don't have a matrix, we have an integral operator here. So this is the kernel of this integral operator. But we can easily convert it into an infinite matrix if we pass from the functions on a circle into the basis of Fourier modes. So I just write any function from H as a sum over half integers of, well, this fp times z to p plus 1/2. So it turns out to be convenient to...
Not sure we can see you writing. Are you writing? Or pointing? I don't see you pointing, or...
and now, do you see it?
Oh, the little arrow. Okay. Yes, thank you. Sorry for interrupting.
Sorry, as long as we've stopped, Oleg, why a half?
Basically, this is in order to be able to treat the subspaces H plus and H minus in a symmetric way.
But the Fourier series doesn't involve a half. Is that, what do you mean by Z then? I mean,
well, you see, I introduce plus 1/2, but I also introduce plus 1/2 here.
I see. Okay.
I mean, of course, the powers of Z should be integer. So this is just the usual Laurent series. But for technical reasons, it is convenient to label the elements of H plus by positive half integers and the elements of H minus by negative half integers. Yeah, so this is basically the picture. Yeah. So you see, this is the matrix K that we had before, and it is infinite in both directions. And so you see that, so this 1/2 here, 3/2, 5/2, this corresponds to first modes of the space H plus. And here we have minus 1/2, minus 3/2, minus 5/2, and so on. So this goes all the way down to minus infinity.
Sorry, Oleg, to define your A minus plus A plus minus, you only need one of the two Riemann-Hilbert factorizations, not the other one.
Yes, right, exactly. So this A plus minus, it's basically here. So this is minus plus, and for plus minus, you have a similar formula. Now, if
But do you
you
need sidebar to define the other one?
no. Here I need only psi plus instead of psi minus here. So see what this operator does is that so you have to multiply some function from h. So this is a minus plus. So you take a function from h plus, so some f plus of z prime here, and you integrate along the circle, and you get, because of the form of the kernel, something which lives in h minus, right?
Yes.
And likewise, you can obtain a similar formula for this operator. Now, if your problem is not isomondromic, it may well turn out that it is this factorization that you have, and it is this factorization that you want or you don't want. You can write an equivalent formula in terms of psi bars if you want. So any of the two factorizations is fine if you want to find tau.
Yeah, Oleg, we won't have a chance to ask you this later. So although you're only talking about the isomonodromic half of your paper, I would like to just ask a very quick question about the other half, the isospectral half. I mean, the Gelfand-Dickey.
Maybe we can discuss this after, because otherwise,
yeah, okay,
Oleg will never finish his lectures.
Yeah, okay. Good
Thank
idea.
you, Jack. Thank you.
Well, but actually, the only place where I use isomonodromy is this place here, in order to show that for specific jumps coming from these linear systems, we can identify the Japanese tau function and this Williams determinant. But this is really the only place. Everything else, including this derivation of the series, at least the derivation of the structure of the series, it is completely independent of isomonodromy. So you will exactly the same structure of the series, even you have an arbitrary jump. Right, so now what is the idea? So now we have to sum all possible principal minors of this matrix. So this means that I have to take some column, let's say, then I have to take exactly the same row, then I have to take maybe I will make two lines here and two lines here for this to be non-trivial. And then I have to restrict my matrix to the intersection of these lines, and then compute the corresponding determinant. Okay. Now you see that these different principal minors will therefore be labeled by finite subsets of half integer lattice. There is just one subtlety here, is that so far I have ignored the matrix structure of these elements. So we don't only have the Fourier index, which is half integer, but each of these is actually a 2x2 matrix. So this coming from the matrix structure of the Riemann-Hilbert problem that we are solving. So this means that in addition to this half integer indices, we will have colors, say red and blue, and the different principal minors will be labeled by red subset of half integers and a blue subset of half integers. So I think that, well, probably some of you, maybe most of you know that these finite subsets of z plus 1/2, they can be naturally represented by Maya diagrams, and Maya diagrams can then be converted into Young diagrams. So after all, the structure, the combinatorial structure of the expansion of this Widdom's determinant has the following form. So we have a sum over integers, a double sum over Young diagrams, and here we have these products of, so basically what we have here is a principal minor of our matrix, which factorizes because we have one block from here and one block from here. So let me.
Is this just Cauchy-Binet?
Maybe yes. Yes, I think it should be Cauchy-Binet, although, well, maybe I can confirm you later.
I mean, it's a combination of the Van Gogh and Cauchy-Binet.
Yeah, so anyhow, let me stress once again that this summation, so this combinatorial structure is valid for any jump, not necessarily isomonodromic, but in the isomonodromic cases, not only we have these hypergeometric expressions for psi plus and psi minus and this operator A, but moreover, we can compute this this elementary summons completely explicitly in a factorized form. So this is an additional miracle which happens in the isomonodromic situation. So now if we
just to slip in, Oleg, a quick question before you scroll down. Is it true that in the isomonodromic case, both of these two determinantal factors depend on the deformation parameter T? However, in the isospectral or the Gelfand-Dickey case, the first depends on T and the second depends on the element of the Grassmannian.
Already for the isomonodromic case, this is not quite correct statement. So basically, I can put the dependence on T is trivial, I would say. So I can put it either in A plus minus or in A minus plus, or I can split it between the two. So the statement is that if you have here some element, let's call it A P Q or minus Q, because this is minus indices. So this matrix element will have behavior like T to P plus Q times a constant independent of Q. Okay. So I can move the dependence on T from here to here if I want by doing some conjugation. And this is basically why this expansion is interesting, because in a sense, this is a serious expansion in powers of T. So the more, the bigger is the size of minors that we take, the smaller is the corresponding contribution to the tau function because of this property. Right. And so now let me just show you, or rather rewrite for you once more the expansion of the tau function of Painlevé 3. So I take Painlevé 3, the most degenerate version of it, just to minimize the number of parameters. So the solution of the corresponding equation.
You mean D8, yeah? Painlevé 3 D8.
Yes, so this is Painlevé 3 D8. So I don't want thetas to appear in the formulas, so I take just parameterless Painlevé 3. So the solution of this equation should depend on two integration constants, on two monodromy parameters, and they appear in this way. So these letters that I call sigma and eta here. So basically what I have done, I took this formula, which was a summation over integers followed by a double summation over Young diagrams. And then, well, because of a certain symmetry of these minors, it turns out that the result is just a kind of Fourier transform of some function, which depends on the variable t, which is Painlevé variable, and one monodromy parameter sigma, okay, which is, well, sigma is essentially, well, for Painlevé 3, we have this picture here. And sigma is related to the trace of the monodromy matrix along this cycle. So it's 2 cosine 2 pi sigma. And eta is a kind of twist.
Sorry, this is a general solution. So besides the monodromy, there should be two integration constants.
No, in monodromy, you have parameters of the equation, right? And in this Painlevé 3D8 case, there are no parameters. And integration constants. I mean, the monodromy data, they encode simultaneously the parameters of the equation and the integration constant. I mean, monodromy, it also plays the role of initial conditions.
Maybe I just don't know what the D8 thing means. For me, Painlevé 3 has two parameters, two monodromy parameters.
So if you took generic Painlevé 3 and not this D8 thing, then in addition to the sigma and t, you would have here some theta and theta twiddle.
John, D8 is when the parameters which we normally assume not to be 0 are both 0 in the Painlevé 3. So there
actually,
is this product of, I don't remember, gamma and delta that normally we put equal to 1/2. And the D8 case instead is when these two parameters are both 0. So they disappear from.
Okay, so eta and sigma are both integration constants.
Mm-hmm. Yes, and this is now specific for isomonodromic problems. So the previous formula, which is here, is valid for arbitrary jump, but this periodicity you only have in the isomonodromic context. Sorry. So this B is essentially this double sum over Young diagrams. And well, it so happens that this function B that we have computed from the Fredholm determinant, it coincides with the so-called irregular Virasoro conformal block with central charge equal to 1. Okay, so now I'm not sure
But actually, this is something, okay, so I just got a message that you might be given an extra hour if you want it. Now, just if you want it. And may I take this occasion to try and pester you, since we like to do that, apparently, and understand exactly how this step works, because this is for me mysterious. So there is some combinatorial stuff, some Maya diagram, and then we do some computations, which are very complicated, at least for me. And you find this mythic formula with this B function, and this B function is a conformal block. Could you shed light a little bit on what the intricacies of these computations, and if you are not happy to do that, then could you answer the second question, which is why? Is this just luck, or is there some potent philosophical reason? Maybe we cannot still prove it, but maybe there is something telling us, some idea, some intuition, why we should look at conformal blocks.
It's a rather long story. Okay,
that's
so
where the extra hours come in. I mean, if you like, you could do it next time in 1 hour, but I would and otherwise you'll offer me a tea and you know, we'll talk. I mean, I think it's very important because it's kind of mysterious, you see. It's the beauty of this story is that somehow you are able to import all this machinery.
Well, actually, there are several stories here. So first of all, we have this isomonodromic deformations. Then we have conformal field theory. And there is a third part of the picture, which is, well, supersymmetric gauge theory. Now, the link between isomonodromy and the CFT, well, it is possible to explain, but unfortunately, in my opinion, this link is very hard to make rigorous, mathematically rigorous.
Could I venture a comment?
Mm-hmm.
I think that the answer, I mean, I thought about exactly the same question Martin asked. I believe that if one looks into the computation, that the link between this expansion with the products of the parts labeled by partitions and so on, and the conformal blocks are related by the fact that the Cauchy-Binet identity is really the fermionic Wick theorem in disguise, and that's really what you're recovering.
I'm afraid that that's not helping me. Sorry, it's too much of a learned explanation.
Maybe I could say
let me try to say a few words about this error. So the point, the important point here is that conformal blocks of this Virasoro or Lisovyy CFT, they are known to satisfy some linear differential equations. And these conformal blocks, they solve by their very constructions a certain quantum Riemann-Hilbert problem. So imagine something like SL2 Riemann-Hilbert problem, but with operator-valued monodromy matrices. So these CFT objects, they solve a kind of this. And what happens for C equal to 1 is that you can, precisely by this Fourier transform, you can make the operator valued monodromy matrices just the usual ones, numeric. And this is basically the reason why this arrow works.
So is this perhaps then the same statement as saying that we have some monodromy group, then we have some quantum algebra corresponding to this monodromy group when we quantize? This is double affine algebra, whatever, and then in certain cases, then we can go down again. So when Q is equal to 1 or C is equal to 1, this object becomes the classical object.
Exactly.
So in a sense, I should, to see this arrow for all the Painlevé equations, I should take the Painlevé equation, take the linear problem, quantize, which will give me some KZ or confluent KZ equation, do the consider the quantum monodromy, and then in some limit I obtain this isomonodromic, but on the other side I have this CFT.
Yes, I think this is close to what actually happened. So the object that I wrote here, so a 4-point conformal block with one degenerate insertion sitting in Z. So these guys, they have a monodromy, which provides a realization of your favorite double affine check. So this C1 check, C1, or whatever you call it. And then for C equal to 1, this quantum monodromy diagonalizes, and you get the solution of the numerical Riemann-Hilbert problem. But this does not answer why do we have these combinatorial formulas? So in CFT, you don't have, so you can compute conformal block as a series in powers of this T variable, but you cannot give a general formula. You can just compute the series order by order. Okay. And this explicit formula, it first came not from CFT, but from gauge theory, which happens to be related to CFT by, well, so this is called AGT correspondence. So it identifies some special functions which appear on this side and conformal blocks of Virasoro algebra. And this is very non-trivial. Okay. But once you have done this, you have an explicit expression for conformal blocks, which you can use for isomonodromy. Now, of course, it would be nice to also have this arrow here, but at least to my understanding, this is not clarified yet. So what we do is in order to get this sums over partitions is that we go from here to here and then to here. Now,
Thank you. This, I think, is very inspiring. Thank you.
But on the other hand, one of the points that I would like to emphasize is that in order to obtain this formula, you actually don't need to know anything about CFT or gauge theory. So what I am doing is just expanding a determinant in the sum of principal minors. So all this combinatorics is just about labeling basis elements in the space of functions on the circle. That's it. So even fermions we don't need. Okay, so let me maybe jump over this conformal block stuff. So there is this scheme that I have already shown you before. So we have just seen an.
Sorry, Oleg, I will interrupt you, but we are very serious about your force talk. So if you want, you may not jump over this stuff.
Or maybe what he can do if he's not ready, he can continue this, and then next time he's going to go back to what is jumped up. Whatever you like, Oleg, you feel free.
Yes, Oleg, you have a slot, fortunately.
Oleg, it would be really great if indeed you can make it. So we're very serious, as Leonid said. So it means that you now can a little bit feel more relaxed.
Okay, okay. So then let us discuss conformal blocks a little bit. So perhaps for experts it will be not so interesting, but
do it for me, Oleg. Think of me, I know nothing about conformal blocks, nothing. Okay.
Okay.
Thank you.
So we start just from the Virasoro algebra, which is a Lie algebra with an infinite number of generators labeled by integers. So we have these LMs, which satisfy these commutation relations. And this algebra contains a central element, which for us will be just a number. So we treat this C, the central charge, as a complex number. And we will consider two types of representations of this algebra. So the first type of representation will be highest weight modules. And their construction is precisely like what you know for SL2, right? So for SL2, you have some highest weight vector, which is killed by, so in SL2, you have L plus, L minus, L naught. So you start from some vector which is killed by L plus. And then you want this vector to diagonalize L0. So this is the highest weight. And then all the other vectors of this representation are generated by the by L minus. But in the Virasoro case, you have many creation operators. So a typical vector from here, from this highest weight module, will be something like that. So you have delta, and then some power of L minus 1, some power of L minus 2, some power of L minus 3, and so on.
Sorry, Oleg, I know you're discussing Virasoro on its own, and you're not pinning yourself down on the representation, but should we be thinking of these Dirac ket states as either fermionic or bosonic Fock space?
No, actually, fermionic spaces will be sums of these highest weight modules. So a fermionic representation breaks into a direct sum of these highest weight modules, but I am not going to discuss that. Yeah, so we have an infinite dimensional space of states of this form, okay, which is labeled by a complex number delta. Okay. Now we will also consider what is called Whittaker module. I will take just the simplest possible example. So here we should start from a Whittaker vector, which is a joint eigenstate of the annihilation part of the algebra. That is a joint eigenstate of these generators with negative indices. Sorry, with positive indices. And now you see that here I picked the simplest possible eigenstate of this form. So I suppose that all of the eigenvalues for L2, L3, and so on, so they are 0. And the only non-trivial eigenvalue, which will play the role of this Painlevé variable t, is the eigenvalue of L1. And the other basis vectors, they are generated just as before by creation part of the algebra, but there will also be powers of L0. So a typical vector in this module, it will have a form like this. So L0 to some power, L minus 1 to some power, and so on. Okay. Now, between these two modules, there is a canonical pairing. Well, actually, between Whittaker module and the dual of highest weight. So this pairing is fixed by the requirement that which is written here. So basically, you can you ask that the action of the generator Lk on the vectors from the Whittaker module can be transferred to the vectors from V without changing the pairing. So this may sound a little unclear if this is the first time that you see this type of computation. So let me just show you an example. So suppose we take a Whittaker vector W of t. We put here some generators representing so we take some vector from the Whittaker module. And we want to compute the pairing of this vector, the scalar product of this vector, with some vector from here. So we have something like, I don't know, L1 to the power 11, and here delta. So what you are going to do now is that you want to transfer the action of L-1 and L0 on this vector here using the commutation relations of the Virasoro algebra. And you want to transfer the action of L1 here because you know, let me show you once again. So you know how the generators with positive indices act on W, and you know how the generators with negative indices act on the dual of this delta. So basically, this is all about computing, about using commutation relations between the generators. So after all, what you are going to get is that so this expression is given by some function, polynomial function of delta and the central charge and the square root of t times a pairing like this one. But again, so this is very elementary computation. For each of the matrix element you would want to compute.
I think your normalization condition must be like pairing of delta and W is 1, but not 0.
You are right. So this is wrong. Yes, so this is 1 or any other number, actually. So this is just a normalization. It's important to have here something non-zero, but otherwise it's not so important. Right, and now conformal block. So this simplest irregular conformal block that we need for Painlevé 3D8 is just the norm of this Whittaker vector. So now you can ask me, well, how can I compute the norm if I don't have a pairing between different vectors from here and from here? But, well, basically the idea is to insert between these two the identity operator, which is viewed as an element of this product, of the highest weight representation and its dual. And now you can compute. Now you can compute because you can compute any of those matrix elements. And when you do the computation, well, at low orders, it's not so difficult to obtain explicit expressions. But the further you go in order, well, the harder the computation becomes. So if you really want to understand how does it work computationally, perhaps the best exercise one can do is just to replace the Virasoro algebra by SL2. So you restrict these two subalgebra generated by L0 and L plus minus 1, and then try to compute this B, so this norm of the Whittaker vector along the very same lines. The advantage is that in this case, you can do everything very explicitly because essentially the structure of the highest weight and the Whittaker module is much more simple. You don't have many generators like this. You just have vectors like L minus 1 to the power m times delta here, and you have something like L not m L minus 1 n times w of t, so the vectors here. And so the exercise is to check that the corresponding conformal block for SL2 is nothing but the Bessel function. So you basically can compute every term in this series explicitly and recover the known coefficients of Bessel. Right, and so in our story we will need two special values of central charge. So one value I have already mentioned. So this is C equal to 1, which is relevant for Painlevé. And there is also a very interesting quasiclassical limit. So this quasiclassical limit corresponds to sending the central charge and also this delta, the conformal dimension, to infinity, but in a correlated way. So basically we require that when both go to infinity, the ratio of delta and C remains finite. And the argument of this conformal block, so the variable T here, it also goes to, but not to infinity, to 0. in a way which is correlated with delta and C. So this is basically the formula. So you see every argument of conformal block depends on a parameter which I call B. So C goes to infinity, delta goes to infinity. So this T variable also goes to infinity. To infinity. And then we have a conjecture which, well, everybody believes, but I think that it was never proved rigorously that this in this limit, this conformal block has this WKB type asymptotics. So you see, if you take the logarithm of the left-hand side, then it diverges as 1 over B squared.
What do you have in the numerator? What is f of sigma s?
And this is what is called a classical conformal block.
And is that related to some representation theory as well?
At least not directly. Let me stress once again that, first of all, this equality is a conjecture. So it is a kind of conjecture and simultaneously a definition of this F.
So you're saying that the conjecture is the fact that it goes like exponential of 1 over B square, and then you define the coefficient of that 1 over B square to be the classical conformal block.
Exactly.
Okay.
But even to make that statement precise as a conjecture requires some explanations. So you see conformal block, which is on the left-hand side, is a series, is a power series in this variable. So now what you do is that you take the logarithm of that, you consider it as a formal power series, and then the statement is that, well, every coefficient of this formal power series behaves like 1 over B squared. But I'm not quite sure that you can make an analytic sense of this statement. So I mean, this tends to this as a formal power series. Okay. Right, so this is a conjecture, and so these two values of central charge, c equal to 1 and c equal to infinity, they are relevant to two inverse monodromy problems that we were discussing. So c equal to 1 gives the solution of Painlevé 3 with this formula here, and this c equal to infinity case is again conjecturally related to the accessory parameter function in Mathieu equation. So perhaps you don't, well, actually my notation was different before. So before we had Mathieu equation written in this form. plus maybe 2 lambda squared cosine 2x psi equals to e psi. We considered a Fouquet substitution which had this form, Fouquet or Bloch. So something like this. And we had the following question. So we wanted to have the energy as a function of lambda, or the coupling constant in the potential, and the mu, which is monodromy parameter. So this lambda is more or less S. So maybe S is yeah, probably square root of lambda or something like this. And sigma is this Fouquet exponent nu. Okay. But this is precisely this function that we were computing in the very first lecture with continued fractions. And so one way to convince yourself that these two conjectures are true is the following. So you just take this function b, which you can compute an arbitrary number of terms, say up to t to power 10 or 20 or 50. Then so you take the logarithm, you expand, you extract this asymptotics, and then you compare the result with the this continued fraction expansion of the accessory parameter in Mathieu. And you see that the two results coincide. And well, there are reasons for that, but well, once again, this is a conjecture, and I'm not sure that this conjecture is easy to prove.
It looks like some sort of duality, which you see, for example, in Daha. I don't remember now this example of Painlevé 3, but for example, for Painlevé 5, we have that we have a duality between quantum dual Han polynomials and quantum BQ Jacobi polynomials. And these are precisely two different limits of Askew-Wilson polynomials, in which you have a game like this, in which in one case one parameter goes to 0, to 1, whatever, and the other one goes to infinity. Maybe, just guessing. It looks like one.
It would be nice, and this is a good remark, but this is perhaps more close to what I am going to discuss next. So you see, when we are working with conformal field theory, we necessarily end up with some conjectural statements. But now, so we have a rather well-known connection between Painlevé and Mathieu equation, or between Painlevé 6 and Hoyne. So we discussed this a little bit in the first lecture. And so what we can ask is the following. So just forget about CFT. So we have a function B here, which is very well-defined convergent series and so on, given the general solution of this. We have a function f or E, so this accessory parameter, which is essentially known from the end of 19th century. So you open Abramovich-Stigan or DLMF or whatever, you find a series for this function. So the question that I want to ask is, can we relate B to F? Can we express B in terms of F or F in terms of B? Yeah? And in particular, I want to understand what is F what is accessory parameter function f for Painlevé 3. Okay, so this is the question that I want to address in the next part. But now I'm not sure. Perhaps I now have to stop for today, right?
It is 4 o'clock UK time, which means 5 o'clock French, and I don't know for John what time it is, but it's somewhere in the morning.
It's 11 o'clock. 11 in Montreal, 10 in Indiana.
Okay.
But
So-
Oleg, right, that you're going to explain that F is classical action along the corresponding solution.
Exactly. So this is the main statement. So yes, perhaps the announcement I can make already. Okay, so on the space of monodromy data for Painlevé 3, you can introduce two types of coordinates. So one pair of coordinates is this sigma and eta, which appear in this Fourier type representation of the tau function. But a different pair of coordinates can be used, which are S and E. So S is a movable pole of this P3 function, and E is some first non-trivial coefficient of the expansion of this function near the pole. Now, F, so the function F is a generating function of the canonical transformation between these two pairs of coordinates. And using that, we will establish very concrete, explicit identities relating F and B. So this is an example of such an identity, which, okay, once again, they allow to express F in terms of B or B in terms of F, if one wants. So knowing the solution of Mathieu equation, you can compute the solution of Painlevé 3 and vice versa. This will be the main message.
Okay, thank you very much, Oleg. Are there any, shall we clap, Oleg, 1 second, maybe? Do I have anybody clapping with me, or am I the only one?
Yes.
Okay, and
You did it for us.
yes, and then if there are more questions, please ask them, unless they are long, and then we will be able to do them after we do the second.
Am I right that the next time we have Oleg, and then the next week we have Arini? Just